So for in class, chapter 2.6, we're going to graph functions. And so our objectives are to recognize basic functions and to apply vertical and horizontal shifts to different functions. We're going to apply vertical and horizontal, what they call shrinking and stretching, and we're going to see it applying to getting closer to an axis of symmetry or moving away from the axis of symmetry. We're going to apply reflections across the x and y axes, and then we're going to summarize the transformations of graphs. So here are our basic functions. We have the linear function, which is y is equal to mx plus b. Here it is. And we have a constant function, which is just a constant over the y axis, which is a horizontal for a particular y value. And then we have the identity function, which goes through the origin, which is nothing more than a line. The quadratic function is a parabola, which we have looked at before. And the cubic function is kind of snake-like. It goes through the origin and it increases very rapidly on the positive side and decreases rapidly on the negative side. Here's our typical square root function, which is the square root of x. Starts at the origin because you can't have a negative square root. We have a cubic function, which is just a snake on its side. And then we have the absolute value, which has a symmetry, in this particular case, right at the origin. And then we have what's called the reciprocal function, which is 1 over x, which is the function that we see here. And it has what we call asymptotes along the horizontal and the vertical axes. So once we've studied our functions, we will now use those functions to create vertical and horizontal translations of those functions. So once we have a function defined by f of x, we can let c and h represent positive real numbers. So when we graph the function, the original function plus some constant, we will be shifting either upward or downward along the vertical y-axis. So the graph of y equals f of x plus c is the graph of y equals f of x shifted c units upward. Likewise, if it's the graph of y equals f of x minus c, we're graphing c units downward. So the horizontal shift is where we apply it directly to x within the function. So the graph of y equals f of x minus h is the graph of f of x shifted h units to the right on the x-axis. And the graph of y equals x plus h is the graph of y of f of x shifted h units to the negative x direction. So in example 1, we're going to graph the functions g of x is equal to the square root of x plus 2. And we're also going to graph f of x square root of x plus 2. So we'll see the difference. So here we have in the table, we've gone through and done x equals 0, 1, 2, 3, and 4. And we've looked at the parent, which is y is equal to the square root of x function. And you'll notice that the graphs represent the parent function. Now we look at the families where g of x is the square root of x plus 2. We notice that in this particular case, our graph actually starts at 0, 2. So now it moves up 2 places up for g of x. And now our function is just completely moved in the same direction, but it's just up. So when for example, when x is 1, I have 3. When x is 4, right, I have that the square root of 2 plus 2 is not 4. Yeah, it is 4. So when we get to 2, we're now at 4. I mean, when we're at 4, 1, 2, 3, 4, we're at 4. So this function, the blue function, is my g of x function. So it's just moved up 2 positions. Now if we look at the square root of x plus 2, now we see that when x is a negative 2, we start out at 0. So when x is a negative 2, we start out at 0. When x is a negative 1, it's at 1, right? When x is 2, we're going to be at 2. So now this function looks really like this. Okay, so now you can see that the functions have just moved over 2 positions to the left when we have the square root of x plus 2. So it moved in this direction. So in example 2, we're going to graph the functions h of x is equal to x squared minus 2 and kx is equal to x minus 2 squared. So in this case, the parent of the functions is y is equal to x squared, and that's a parabola, which we have over here showing you on the right hand side of the screen, where we have h of x and k of x, and we see the parabola. And so again, we can use the points to put in the areas where the function will actually go through those points. And so we've done that with the parent functions. Now we're going to look at h of x is equal to x squared minus 2. In this particular case, you'll notice that the function is going to be moving in a particular direction. So when it's the function minus 2, it is going along the y-axis. So notice now that the vertex is going to be 2 units down. So it's going to start at negative 2, 0. And the function is going to move up from there. It's going to be the same function, except it's just moved down 2. So when x is when x is 0, we're at minus 2. When x is 1, we're at minus 1. So we've just moved that whole thing down by 2. And now when x is 2, we're at 2. So when x is 2, we're at 2. When x is minus 2, we're at 2. And so now our function looks like this. We've just moved it down by 2. There it is. Now we're going to look at when we're applying the negative 2 within inside the function, right? X minus 2 squared. So this time around, we notice that we start at the origin, but now we're going to move to the right 2 positions. So, to the left 2 positions. So we're going to actually start here. So when x, I'm sorry, this is a negative 2. So we're moving to the right 2 positions. I was right the first case. So we're going to move over here. When x is 2, we're at 0. So now this function is going to move over 2 spaces. So now you can see that when x is 1, we're at 1. When x is at 3, we're at 1. We can see that when x is at 0, we're at 4. And when x is at 4, we're also at 4. So the axis of symmetry is moved as well. It's moved over 2 positions as well. So in example 3, we're going to look at 2 more functions and we're going to graph. And this time, we're just going to pick out the best points that we can to graph the function. So here is a parabola because it's a quadratic. Here it has z of x is equal to x plus 1 squared minus 4. And so the vertex at this point is going to be the horizontal shift of -1 and the vertical shift of -4. The horizontal shift of -1, the vertical shift of -4. So I come over -1 to 4, 1, 2, 3, 4. And this is where the parabola is going to start. So we know the parabola is going to go positive from this point forward. So now we say, okay, what's the next point? Suppose x is 0. Well, when x is 0, then we're at y is 3. So the actual symmetry of the parabola is through the vertex point. So now I know that there's got to be an equal distant point on the other side of the symmetry line of the parabola. And so now I can go further up. It doesn't matter if I go to x is 1 and I say I square 1. I get 1 plus 1 is 2 and I square it. I get 4 and now I'm at 0. And likewise, I have a symmetry point here at -3 because I get a -3 plus 1 is a -2 and I square it and I get a positive 4 and I'm at 0, right? So those are my, what are those called? That is my x-intercepts, right? And we could have solved for the x-intercepts actually. So that's one thing we want to do is we want to find the y and the x-intercepts on some of these graphs. It's easy to graph by knowing that. Okay, so now we have an absolute value function, and it also has a vertex, and it's at 2, 3. So if we go over 2 and we go up 3, 1, 2, 3, here is our vertex point, and it has a line of symmetry, right? There's our line of symmetry. And so now we just start picking some points. One of the easiest points is let x equal 0. That's going to be our y-intercept. And so when we do that, when x is 0, we have a -2, but the absolute value of a -2 is 2, and 2 plus 3 is 5. So we come up to 5, and we have a point here. So along this line is our symmetrical point, and now we can pick out a point here, right, which is at 4, right? So if we go to 4 and we put x as 4, we also get 2, and the absolute value of 2 is 2, and we add it to 3, we get 5, and here is our, there is our new graph, right? So the book talks about vertical shrinking and stretching, and this is not as important as the vertical shifts and horizontal shifts in some sense, because we're just multiplying. We're doing a multiplying factor either on the function or on x. So for a vertical shrinking or stretching, if a is greater than 1, and so therefore we multiply a times f of x, what happens to the function is it gets stretched vertically by a factor of a, which means that the function gets closer to its line of symmetry. And we'll talk about it. In other words, it gets closer to the y-axis. If the a is between 0 and 1, in other words, it's a fraction, and we multiply it by the function, if a we multiply by the function, we actually start shrinking vertically by a factor of a. And what that means is we get further away from the axis of symmetry. We get closer to the horizontal of the coordinate system. So in example 5, we're going to graph the functions f of x is equal to 1/4 x squared and g of x is equal to 4x squared. So you may want to pause this to see if you can graph the functions 1/4 x squared and 4x squared. So try to do that. So in this particular case, we're going to graph the first one. F of x is equal to 1/4 x squared. Again, the vertex is at the origin, so we know that we have the origin at this point. So now we just need 2 additional points. One is if we go to 2 and we square it, and it's 1/4 of that, we know it's at 1. So notice what's happening to the graph. It's moving away from the axis of symmetry. So we know that at -2, which is symmetrical, it's over on the other side. Then if we go to 4, and we square 4, and we get 4, right? So at 4, we're at 4. So 1, 2, 3, 4. And at -4, we're also at 4. So now we can see that this graph, which is our 1/4 x squared, is moving away from the axis of symmetry, right? And that's what they call shrinking. It's moving away from the axis of symmetry. So now we're going to do g of x is 4x squared. Well, now when you let x equal 1, right, we start at the origin again, and this time this one we're going to put in black, right? So when x is 1, we're at 4. 1, 2, 3, 4. And this function starts looking like this. So now we're moving towards the y-axis, right? So this one is 4x squared, and the other one was 1/4 x squared. You can see how these functions work now. So we're going to talk about the horizontal shrinking and stretching, and we consider a function defined by y is equal to f of x. Let a represent a positive real number. On the horizontal side, if a is greater than 1, then the graph of f of a of x is the graph of y equals f of x, getting further away from the horizontal by a factor of a. If if a is between 0 and 1, then the multiplication of f(a) of x is the graph of y equals f of x that's getting closer to the horizontal x-axis by a factor of a. So in example 6, we're going to graph the functions r of x is equal to the square root of 5x and s of x is equal to the square root of x divided by 5. And you see our table here. We have the parent group, which is y is equal to the square root of x, and we've graphed that onto the graph on the right hand side. Now we're going to look at r of x, and we see that it starts at the same point as the parent, right? It starts at 0, 0, and we're going to put it in blue. Now we're going to come over and we're going to say, okay, suppose x is 5. 1, 2, 3, 4, 5. Then we have the square root of 25, which is 5. So 1, 2, 3, 4, 5. So this function is going to go at least up through that point. So you know it's now moving away from the horizontal. It's moving away from it. So this is where they call it shrinking. But what we're going to do is we're going to go 1/5. So suppose x is 1/5. It's going to be at 1. So that's going to be about right here. So this line is going to go up like this. Right? So now we're moving away from the original function when we multiply by 5. Okay? So I suppose in this case we're expanding it, right? So now we look at s of x and we say the same thing. Suppose x is 5. Well, if x is 5, we have the square root of 5 over 5, which is 1, and the square root of 1 is 1. So when we come over to 5, 1, 2, 3, 4, 5, we're at 1. And here I'm going to put this in black. So we start out at 0 here, but now we're going to go at 1 here, right? And so you can see automatically that now x is going to be pretty small. It's going to come around like this, right? So s of x is this function right here. We don't have to be we have to be okay with this. I mean, it's not something, you know, we have to just to approximate. But you notice that in this particular case, what's happening to my function when we divide by a fraction of the function, what we're doing is we're moving away from the original function and we're getting closer to the horizontal. In example 7, we are using the graph on the left of f of x to graph a new function y is equal to f4 of x. So we have on the left-hand side graph of f of x, we've looked at the graph and we have the ordered pairs of this graph. So as you can see, we have the ordered pairs of the graph, -3, 1, -1, 1, 0, 0, 4, -3, and 6 and 3. Now, what we can do is we can divide the x ordered pair of the original graph by 4, and when we do that, we will get the x values for the new function. So when we do 4 divided by a -3, we would get a -3/4. If we divide a -1 by 4, we get a -1/4. If we divide 0 by 4, we get a 0. If we divide 4 by 4, we get a 1. And if we divide 6 by 4, we get 3/2. We also notice in this particular example that we can also create a few of our own ideas. So we will go ahead and plot the points. So in our case, we have 1, -3. So at 1, -3, we have 1, 2, 3. We have a point here. And we have a point at 0, 0. We have a point at -1, -2. We have a point at 3/2, 3. 1, 2, 3. And we get the values for y from the original pair set. So what has happened is the function has, it's like an accordion, it has been squeezed. So the original function has been squeezed down to these values. So our fourth objective is looking at reflections across the x and the y-axis. So we're going to consider a function defined by y is equal to f of x. So the reflection across the x-axis is the graph y equals minus f of x, is the graph of f of x reflected across the x-axis. And then we're going to look at reflections across the y-axis, where the graph is nothing more than a mere image of itself over on the y-hand side, on the left-hand side from the right-hand side. So the graph of y equals f minus x is the graph of y equals f of x on the other side of the y-axis. So in example 8, we're going to graph the function f of x that is given by the graph in the top right-hand corner. So we're going to regraph this one by graphing y is equal to a negative f of x. So we know that this was reflected on through the x value. So we go to 0, 0 is going to be the same. So we put in the point 0, 0. And now we look at the point 1, 1 up at the top. And now if x is 1, we have a negative 1 over here for 1. If x is 2, we have a negative 2 here. If x is 3, we have a negative 3. And finally, we have a negative 4. So you can see that the image is essentially, or the function is passed through the x-axis on the other side, right? Now we'll look at the y value. And so in this case, for a value of x, now we're looking at a negative x. We still have 0, 0. But now we have for a negative 1, a negative 1 is a negative 1 is a positive 1, which is 1 and 1. So now we have a negative 2, and a negative 2 times a negative of a negative 2 is a positive 2, which is a positive 2 for y. Now we have a negative of a negative 3, which is 3. And now we have a negative of a negative 4, which is 1. So now this is a mirror image through the y-axis of the original. Oh, I guess it's x. Oh, I made a mistake. It's x2. Sorry. Goes down to 2, and it should have gone 2 here too, right? Because it's 4, 2, or 4, 1 actually. So, alrighty. So there's our graphs. So it's important to summarize the transformations of graphs. We're going to perform the horizontal transformations first. These are operations on x. And then we perform the vertical transformations next. The idea here is if we have a function in terms of c and d, typically this is our beginning point for the graph. And what we mean by that is typically that's our vertex, especially if our function is a squared or a squared type of function, or it's an absolute value function. Then we take a look at if we're going to do the transformations from the vertices. Typically, I don't always rely on this stretching and shrinking method, but I rely on x-intercepts and y-intercepts if they exist. And typically, y-intercepts usually always exist unless they are one of those reciprocal functions, but there are usually a y-intercept. Not always. Not always. Okay. So here is the order of transformations. It talks about a horizontal shrink, stretch, and reflection of B. So in other words, the factor that's multiplied by x, we usually handle that one first. We do handle the horizontal shift. We can always handle the horizontal shift and the vertical shift because they may be the beginning points of our function. And then from there we can see whether or not the function is closer to the axis of symmetry or if it's further away from the axis of symmetry. Yes, so in example 9, we're going to graph the function defined by f of x is equal to 2 absolute value x plus 1 minus 3. So we will notice that the parent function is f of x is equal to the absolute value of x. And we note that our function looks like this. We see that the vertex is at 0, 0. When we look at this function over here, we notice that we have to move in the x direction to the left by 1, so that's a negative 1, and we move down 3 from the origin. So essentially, this point will move down to this point here on our new graph. So on our new graph, we move over negative 1 to a minus 3. So our vertex is going to start there. Why does that work? Well, suppose x is minus 1. Minus 1 plus 1 is 0. 2 times 0 is 0. Minus 3 gives us that point. So from that point, everything else is positive because that's the lowest point possible. So that's where our vertex is at. Now, the next point is I'm going to create an axis of symmetry because I know this is an absolute value. I can go along this line here, which is where my vertex is at. And now I'm going to pick an easy point. I'm going to pick the point that's the y-intercept. Well, that's easy because the y-intercept means that x is 0. And so now when x is 0, I have 2, absolute value 0 plus 1, absolute value minus 3, and I end up with 2 minus 3, which equals negative 1. So my y-intercept is at negative 1. So I can put that in there, negative 1. And because I have an axis of symmetry, that means that the next point has to be at negative 2, negative 1. Well, let's try it out. I put a negative 2 in, I get a negative 2 plus 1, I get a negative 1, but the absolute value of a negative 1 is 1. So 2 times 1 is 2. 2 minus 3 is a negative 1. So again, that's where that point is. Now, I can just draw my graph. There it is. And you notice now that this graph is closer to its axis of symmetry than the original parent function. Why is that? It's because of the 2. So now we're going to graph this next function. This is example 10. So z of x is equal to a negative 1/2 square root of 3 minus x. Well, the starting point under the parent function is at 0, 0. At 0, 0, we start this function and we see when x is 1, y is 1. When x is 4, y is at 2. Right? So now we know how to draw this line. So now we take a look at this function and we say, well, where does this function begin? Well, can x be positive? Well, it can be positive only up to 3, right? Because at 3, the square root function is at 0. So this function begins at 3. Now, here's where we have to be careful of. This is a negative. So that means we're going to be flipping the original idea over through the x-axis, right? We're reflecting it through the x-axis. But furthermore, x has to move in the negative direction. Why? Because suppose I put a positive 4 in for x. 3 minus 4 is a negative 1. We have the square root of a negative 1. That's I. We can't graph that. So x has to move in the opposite direction. So now we'll pick a point. Suppose I say, okay, so let's x be 0. And then I have the square root of a negative 3 over 2. But I don't know how to graph that exactly. So I'll pick a point that seems a little easier to deal with. Suppose I pick x is 2. If x is 2, I have 3 minus 2, which is 1. The square root of 1 is 1. And so then I have a negative 1/2. So when x is 2, I have a negative 1/2. So I have a point right here. Oops, that doesn't look right. I've got to be more careful here. So I need to put the x right here. Yeah, that's not even good. I've got to get better at this. My points are off usually. Okay, there we go. And now I'm going to pick another point that's easy. So suppose x is a negative 1. So a negative of a negative 1 is 1. So 3 plus 1 is 4. The square root of 4 is 2. And 2 divided by 2 is 1. So I have a negative 1 over here. So I have a point that goes through here. And so now I have a graph that looks like this. Right? So here's what my graph looks like. The best it can be. Okay? Notice it's flipped and it starts on the negative side. It starts at a 3 and goes to the negative. So in this case, we know what the domain is. The domain for x, right, is what? Negative infinity to 3. And it can be 3, right? That concludes our section 2-6. Please review the problems in the book and also work your assignment problems as well.